4 humans just flew farther from Earth than any person has traveled in over 50 years. And the thing that had NASA scientists watching every single second was not the rocket engine. It was not the lunar flyby. It was something invisible, silent and deadly. And the crew flew straight through it. The Van Allen radiation belts, 2 rings of trapped high-energy particles surrounding our planet like invisible walls of atomic shrapnel. Every mission headed to the moon or beyond has to pass through them. The Apollo astronauts passed through them. And on April 1st, 2026, Commander Reed Wiseman, pilot Victor Glover, mission specialist Christina Koch, and Canadian astronaut Jeremy Hansen flew straight into them aboard NASA's Orion spacecraft, named Integrity. This is the story of what radiation actually does to a human body in deep space. It is the story of what NASA built to stop it. And it is the story of whether the systems worked. Because as of today, April 10th, 2026, this crew is splashing down in the Pacific Ocean after 10 days beyond Earth's magnetic protection. The data is coming in, and it tells us something critical about whether humans can actually survive the journey to the moon and eventually Mars. The first thing you need to understand is that radiation in deep space is not one thing. It is 3 different threats happening simultaneously, each one with a different character and a different way of trying to kill you. The first threat is the Van Allen belts themselves. Charged particles trapped in Earth's magnetic field, compressed into 2 intense rings surrounding the planet. They are brief, but brutal. Orion crosses them quickly, but the dose rate inside those belts is unlike anything an astronaut experiences in low Earth orbit. NASA's own data showed that during one passage through the belts on Artemis II Orion, simply changing the spacecraft's orientation during an engine burn reduced measured radiation levels by nearly half. The belts are that directional, that intense, and that unforgiving if you approach them wrong. The second threat is solar particle events. The sun is not a stable, predictable object. It erupts. It launches coronal mass ejections, giant clouds of solar plasma hundreds of times the size of Earth, accelerating particles to near light speed. If one of those events hits you while you're beyond Earth's magnetic shield, radiation levels inside the spacecraft can spike sharply over the course of hours. Too high a total lifetime exposure, and you are looking at elevated cancer risk, cognitive impairment, and disorders that can end an astronaut's career before they ever fly again. The third threat is galactic cosmic rays. These are not from the sun. They come from outside our solar system entirely. High-energy particles traveling at near-light speed from exploding stars and distant galaxies. They are the chronic background noise of deep space. You cannot fully shield against them. They pass through nearly everything, and they are present every single second of every deep space mission, slowly accumulating in the body's cells, whether you are sleeping, eating, or looking out the window at the moon. This is what the Artemis II crew was flying through for 10 days. Now here is the number that frames everything. Over the course of this 10-day mission, the 4 astronauts burned through approximately 5% of their lifetime radiation exposure caps. That is, the cap every NASA astronaut carries with them for their entire career. In 10 days beyond Earth orbit, they used 5% of it. For comparison, spending an entire month on the International Space Station, which sits just a few hundred miles above Earth, still inside the magnetic field, produces roughly the same exposure. The Artemis II crew did that in 10 days in deep space. That number is not a crisis. Scientists describe the total dose as roughly equivalent to a whole-body CT scan, manageable for a 10-day mission. But the number is not the point. The point is what happens when missions get longer, when astronauts spend 30 days on the lunar surface, when they spend 6 months flying to Mars. The math does not stay manageable. It becomes the single biggest unsolved problem in human spaceflight. Researchers at NASA describe radiation as the showstopper, the number one limitation to how far humans can explore the solar system. This is why Artemis II was never just about flying around the moon. It was a radiation laboratory with 4 human beings inside it. The hardware NASA deployed on this mission to measure and manage that threat is unlike anything flown before. Orion carried 6 hybrid electronic radiation assessors, active dosimeters mounted at different points around the cabin measuring dose rates in real time from every direction. Each crew member wore a personal crew active dosimeter on their body throughout the flight. If radiation levels crossed the first threshold, an audible alarm sounded inside the spacecraft and mission control was immediately notified. If levels hit a higher threshold, the recommendation was for the crew to shelter in the most shielded part of Orion and wait it out. NASA also partnered with the German Aerospace Center for an upgraded detector called the M42EXT. This version offers 6 times more energy resolution than the model that flew on the uncrewed Artemis I mission in 2022. It can distinguish between different types of radiation particles with far greater precision, including heavy ions, which are considered particularly dangerous because of the density of damage they cause at the cellular level. And then there was the Avatar investigation, one of the most scientifically significant experiments ever flown on a human spaceflight mission. organ-on-a-chip devices, tiny tissue chips carrying bone marrow cells from each astronaut, flew inside Orion alongside the crew. One chip per astronaut was in space. Its identical twin chip stayed on Earth as a control. After splashdown, scientists will examine how spaceflight radiation and microgravity affected the chips compared to the Earth. Based versions, comparing them against blood and saliva samples collected from the crew 6 months before launch and again after landing. The bone marrow chips are significant because bone marrow is where the immune system is produced. It is where blood cells form. It is one of the most radiation-sensitive tissues in the human body. If the chips show accelerated cellular aging, DNA damage patterns, or immune suppression signals, that data will directly shape how NASA designs protection systems for longer missions. The crew also participated in the Spaceflight Standard Measures study, collecting blood, urine, and saliva samples to document changes in cardiovascular health, nutrition, and immune function. Researchers will analyze whether dormant viruses like the ones that cause chickenpox and shingles reactivated in space during the mission. This has been observed in astronauts on the International Space Station. The difference is that station astronauts are still inside Earth's magnetic protection. These 4 astronauts were not. The space weather dimension of this mission deserves its own attention because it nearly became a genuine emergency before the crew even launched. On March 31st, 2026, just hours after NASA officials said the space weather forecast looked clear, the Sun unleashed an X-class solar flare, the most powerful type known. This was followed by a fast-moving coronal mass ejection. NASA did not anticipate direct effects on the mission, but the timing was a sharp reminder of how unpredictable the threat actually is. The mission launched on April 1st, 2026, right as Solar Cycle 25 was moving out of its peak. Forecasters at NOAA's Space Weather Prediction Center described conditions as still active, still on a roller coaster. The sun had not gone quiet. The Artemis II crew was flying into deep space during one of the most active solar periods in years. Ground teams at NASA Goddard's Moon to Mars Space Weather Analysis Office and the Space Radiation Analysis Group at Johnson Space Center monitored the sun around the clock for every hour of the 10-day mission. 2 thresholds governed the crew's safety. The first threshold signaled a caution and triggered closer monitoring. The second threshold meant shelter. In practice, sheltering inside Orion meant retreating to the most mass-shielded section of the capsule and using the surrounding equipment and water stores as additional protection. Radiation shielding in space is fundamentally about mass. Charged particles slow and stop as they pass through matter. The more mass between the particle and the astronaut, the lower the dose. But there is a complication that makes deep space shielding more difficult than it sounds. For solar proton events, extra material helps. You add more shielding, you reduce the dose. For galactic cosmic rays, the calculus is more troubling. When very high-energy particles hit a spacecraft wall or a human body, they can fragment and generate secondary radiation, including neutrons. Adding shielding material can, in some cases, create a shower of secondary particles on the other side that is worse than the original. This is an unsolved engineering problem. It is one of the core reasons why galactic cosmic rays remain the chronic background threat that NASA cannot fully engineer away. The Artemis II crew flew through this environment for 10 days. They flew through the Van Allen belts on the way out. They flew farther from Earth than any human since Apollo 17 in 1972, breaking Apollo 13's distance record from 1970. They completed a 7-hour lunar flyby on April 6th. They photographed the far side of the moon that always faces away from Earth. And then they turned around and flew back through everything again. The question that the data will now answer is what all of that actually did to their bodies at the cellular level. The results from Artemis I in 2022 gave scientists their first high-resolution map of the radiation environment inside Orion on an uncrewed mission. That data showed the belts were even more directional than models had predicted. It showed that spacecraft orientation during transit could dramatically change exposure levels. It gave engineers a cleaner picture of where the hotspots and the safer zones inside the capsule actually are. Artemis II adds what Artemis I could not provide. Human beings inside the spacecraft, living tissue responding to that environment in real time, bone marrow chips comparing their state before and after deep space, blood samples capturing immune responses, personal dosimeters mapping dose to individual bodies rather than to cabin sensors. This is where NASA's radiation research program crosses from engineering into medicine. The question is no longer only how to shield a spacecraft. The question is how individual human bodies respond to deep space radiation and whether that response can be predicted, managed, or treated. Researchers at Massachusetts General Hospital, Brookhaven National Laboratory, and universities across the country have been using particle accelerators for years to bombard cell lines and animal models with simulated cosmic radiation. They have been testing drug therapies, dietary supplements, and even gene therapy approaches borrowed from radiation-resistant organisms like tardigrades. Some of these interventions have shown early promise in laboratory settings. None of them have been tested in actual deep space with human subjects until now. Artemis II is the first data point. The first time scientists can compare what the accelerator predicted to what actually happened in the body of a real astronaut beyond Earth's magnetic field. The organ chips, the blood samples, the dosimeters, the performance studies, and the saliva tests will together build the most complete picture of human deep space radiation exposure ever assembled. And what the data shows will directly determine whether NASA can responsibly plan for longer lunar surface missions. Whether 6-month Mars transits are biologically survivable with current technology. Whether the radiation problem that sits at the top of NASA's list of human health concerns in deep space has a solution within reach, or whether it remains the fundamental barrier it has been since the Apollo era. Today, April 10th, 2026, the Orion capsule Integrity is re-entering Earth's atmosphere and heading for splashdown off the coast of San Diego. 11 parachutes will slow it from over 300 miles per hour down to a gentle 20 miles per hour. The USS John P. Murtha is waiting in the Pacific to recover the capsule and the crew. After a quick medical check on board the ship, all 4 astronauts will be flown to Johnson Space Center in Houston. There, the post-mission medical testing begins, the obstacle course that assesses how their bodies have readapted to Earth's gravity, the blood draws, the cognitive performance tests, the immune system analysis, and the collection of the organ chips that have been living inside Orion for 10 days and are now coming home carrying whatever biological story deep space wrote inside them. The Artemis II crew survived the radiation belt. They passed through it twice. They flew through the most radiation-intense environment any human has experienced in over 50 years. And they did it with more sensors, more data collection, and more scientific rigor than any mission in history. The mission was not just about going to the moon. It was about learning whether we can keep humans alive on the way there, whether we can do the same on the way to Mars, whether the invisible wall of radiation that surrounds every destination beyond low Earth orbit is a wall that medicine and engineering can break through together. The data is coming. And what it says about 4 human bodies that just spent 10 days beyond Earth's protection will shape the future of human exploration more than any photograph, any lunar flyby, and any record-breaking distance ever could.